what I'd like to do now is I'd like to sort of make sure that we're all sort of staying on the same page. And what I'm going to do is sort of give some summary tables that will help us keep track of all the different variations of the things that we're actually seeing. All right, so let's actually do that. Let's make a list of the table for when we reject the null and when we fail to reject the null. All right, so generally speaking, let me see if I'm going to try building this as a table, a box. So bear with me for just a second while I try to put this together. So what I really want is either a 2x4 or 4x2, which is going to be easier to draw in here. Probably, let's do it as a 2x4 table. I'm going to go like this. All right, so we need to divide this into 4 regions. Okay. So here's the general idea. What we're going to do is we're going to think of our observed data in 2 ways. We either have, so we're comparing our data to the null hypothesis, and either we have a usual result. Okay, so either we end up with a result that we would classify as usual, or we have a result that we would classify as unusual. Okay, so these are the scenarios that we're thinking about. So either we have a usual result. So this again, remember here, the idea at this stage is that we are assuming, and that's the key point to what we're doing here. We are assuming that the null hypothesis is true. We may not believe it, but we're going to temporarily assume that. Okay. So what does a usual result mean? Well, a usual result would mean that the test statistic is not in the critical region. So that's generally what we mean by a usual result. So we have a critical region for our null hypothesis. If the test statistic is not in the critical region, that means it's a usual value. So the flip side of that then would be if we had a value that was in the critical region. Okay, an unusual result is when the critical value is in the when the test statistic is in the critical value. It is in the critical region, pardon me. Okay. So in this context here, what we end up with is, in this case, P would be greater than, oops, try that again. So here, P is greater than alpha. In this context down here, P would be less than alpha. Okay. So if we have a usual result, meaning it could have happened just by chance alone, or in that case, it means the test statistic is not in the critical region, or more specifically, if P is greater than alpha, the probability of our observation is bigger than what we would consider as the cutoff for something happening unusually by chance. In this case, we fail to reject the null. We don't accept it, but we're failing to reject it. Whereas if P is less than alpha, meaning the test statistic is in the critical region, or more specifically, we've obtained an unusual result, then we do reject the null. So in this case, we're saying, sorry, an unusual, so we assume this to be true, but we found something unusual. Therefore, we think there's something wrong with our assumption, so we're going to reject that assumption. So I know that having these tables becomes very useful because there are so many small little variations between the Excel functions that we're using, the different types of tests we're using, the variations of what might happen in the test or the outcomes, and all of these things become helpful to sort of, just like we have that flow chart, these become helpful for us to kind of organize stuff as well. All right, so what I want to do now then is talk sort of about this idea of critical regions and p-values. So when we're looking for critical values, so when we're talking about critical values, and again, we use the critical values for the critical regions. So the functions that we're going to end up using here are the norm sin function, or just the norm in function, or the tinv function. So these are the functions, when we're talking about critical values in critical regions, these are generally the functions that we're going to use for this information to get these. Generally speaking, these will actually give us the critical values, okay? So the point here is that these are actually more likely, so we use these functions to get the critical values. Okay, but the critical values help us distinguish the critical regions. Okay, now for the p-values, the functions that we're going to use to calculate p-values, the functions we use here are the one that we're going to use probably the most is the t-dist function. Okay, that's probably the most common one, but we might also use the norm dist under certain circumstances. And when we're doing proportions, we'll use the binom dist function. So we've got three variations of three different functions that we would use for these analyses. Let's sort of build that table next. So let's do the table. We'll do the table for norm sin for one and two tailed, and we'll do the norm s, and we'll do for the tinv. You would use the normal distribution if you actually knew the population standard deviation. But that's such a rare occurrence that generally speaking, if you're asking a question about the mean, you're in all reality, you're going to be using the t-distribution function. And so let's look at let's do the, you know what, I've just realized this is in my other, yeah, I can do this from memory. I don't need to I'm not going to grab my other stack of notes that has this in it. So let's draw a, so what we're going to do is let's do right-tailed, left-tailed, and two-tailed. And we'll do it for each of t-dist and norm dist. Okay. So we have t-dist and norm dist. I'll do two functions this way. And then we want to do left-tailed, right-tailed, and two-tailed. Okay, so here's what we're going to do. We will do a left-tailed p-value. We will do a right-tailed p-value. These are both situations where we have a one-tailed test. And then we will do the formula for when we have a two-tailed test. Okay. So let's do first with the, so let's do the norm dist function. So that would be generally when we're talking about z-scores. So and then we will agree, let's just go ahead and agree that we are working with alpha. So let's let alpha equal, for everything that we're going to do here, let's let alpha equal 0.05. All right, so the first function we would want here, so go ahead and make these, let's make these green. First function is equals norm sinv of alpha, I'll just put in 0.05. And that would be the function that we would use to get the z-score for the left one-tailed test. This is the formula we would use. Now, you're more than welcome to just kind of use that same formula over here as well and just change the sign. But if you wanted to put it in directly, for a right-tailed test, it would be equals norm sin 1 minus 0.05. In other words, remember, the functions in Excel always calculate the area to the left. So if I want 0.05 in the right, there's technically 95 in the left. So that's why we have to do the 1 minus. All right, now for the two-tailed test. So the way to get the two-tailed value, so the two-tailed value, just remember that it's once you get it, it's a plus or minus value. So the formula I would actually encourage you to enter would be equals norm S inv 1 minus 0.05 over 2. So 0.05 over 2 is taking the 5% and dividing it across the two tails. And this is subtracting it from 1. So this is actually giving us the uppermost critical value, the positive critical value. But once I have the positive critical value, I know that I just change the sign. So the next step is then to take the plus or minus of this value to get the two tails. Because remember, there's a critical value for each of the tails. Let me emphasize that. So we are indeed looking for the critical value. This is going the green values will give the critical value for the z-score. It won't give you the z-score for your test because that depends on the sample mean and statistic and other values. Let me actually say critical value or values, because technically there could be two. Okay. All right, now let's do the same thing. Now let's do for a t-test. So now when we're doing t distributions, how do we get the left and right tailed values for the t distributions? All right, so for this one, we would use let me do this in blue. Let's do this in blue. So the function here is equals tinv, and now I have to give it my 0.05. I also have to give it the degrees of freedom, which would be n minus 1. And in this case, it would be a one-tailed test. So because I'm looking for I'm sorry, I'm mixing up the t distribution function. So t in 0.05 for a left-tailed test, I'd like to use the t in function. The only problem with this, so as I've typed it right now, this isn't going to work. I'm going to leave a little space here because I'm going to actually write this in red on what I'm going to change on this function. So before I quote unquote fix this function, sorry, let me go back in here so I can edit it. So before I fix this function, this will actually give me, this formula is going to give the positive critical value. And if I know it's a left test, I actually know that I want this to be multiplied by -1. So I can actually just kind of put that into the formula. So if I multiply by -1, this will give me a negative value. This part here, these last three characters, you can actually omit that if you always remember to change the sign. Okay, but the problem is the t in function, it always defaults to calculating a two-tailed test. So if I actually want it to give me a one-tailed test, well, that would be the same as sort of taking, if I doubled my alpha, then when I divide it in half, that's the amount that's going to go in here. So if I multiply this by 2, if I multiply this by 2, that will actually give me the left-tailed test. So the t in function for a right-tailed test, I'll type that here, is equals t in 0.05 times 2 n minus 1. That gives me the positive value. So in some ways, getting the two-tailed test is easiest using the t in function, because in that case, you would just type equals t in alpha, which is 0.05, and the degrees of freedom. And this function always defaults to giving the two-tailed value. So it's because of the fact it defaults to the two-tailed value that I need to do this trick here. So this trick here of multiplying by 2, that's how we get it to actually give us the one-tailed test. So here we divide by 2, here we multiply by 2. So again, good set of formulas and good set of cheat sheets to sort of have available when you're doing the critical values.